DAG, the scheduler database contains instances of the runs of that DAG. Big changes to the DAG, such as to the start date and/or schedule interval, may confuse the scheduler, as the changes no longer fit with previous DAG runs. Similarly, removing or renaming tasks will prevent you from accessing the history of those tasks from the UI, as they will no longer match the current state of the DAG and will therefore no longer be displayed. The best way to avoid these issues is to create a new version of the DAG whenever you decide to make big changes to existing ones, as Airflow does not support versioned DAGs at this time. You can do this by creating a new versioned copy of the DAG, that is, DAG_V1, DAG_V2, before making the desired changes. This way, you can avoid confusing the scheduler while also keeping historical information about the old version available. Support for version DAGs may be added in the future, as there is a strong desire in the community to do so. Section 11.2. Designing reproducible tasks. Aside from your DAG code, one of the biggest challenges in writing a good Airflow DAG is designing your tasks to be reproducible, meaning that you can easily rerun a task and expect the same result, even if the task is run at different points in time. In this section, we revisit some key ideas and offer some advice on ensuring your tasks fit into this paradigm. Section 11.2.1. Always require tasks to be idempotent. As briefly discussed in Chapter 3, one of the key requirements for a good Airflow task is that the task is idempotent, meaning that rerunning the same task multiple times gives the same overall result, assuming the task itself is not changed. Idempotency is an important characteristic because there are many situations in which you or Airflow may rerun a task. For example, you may want to rerun some DAG runs after changing some code, leading to the re-execution of a given task. In other cases, Airflow itself may rerun a failed task using its retry mechanism, even though the given task did manage to write some results before failing. In both cases, you want to avoid introducing multiple copies of the same data in your environment or running into other undesirable side effects. Idempotency can typically be enforced by requiring that any output data is overwritten when a task is rerun, as this ensures any data written by a previous run is overwritten by the new result. Similarly, you should carefully consider any other side effects of a task, such as sending notifications, etc., and determine whether these violate the idempotency of your task in any detrimental way. Section 11.2.2. Task results should be deterministic. Tasks can only be reproducible if they are deterministic. This means that the task should always return the same output for a given input. In contrast, non-deterministic tasks prevent us from building reproducible DAGs, as every run of the task may give us a different result, even for the same input data. Non-deterministic behavior can be introduced in various ways. Relying on the implicit ordering of your data or data structures inside the function. For example, the implicit ordering of a Python dict, or the order of rows in which a dataset is returned from a database without any specific ordering. Using external state within a function, including random values, global variables, external data stored on disk, not passed as input to the function, and so on. Performing data processing in parallel, across multiple processes, threads, without doing any explicit ordering on the result. Race conditions within multi-threaded code. Improper exception handling. In general, issues with non-deterministic functions can be avoided by carefully thinking about sources of non-determinism that may occur within your function. For example, you can avoid non-determinism in the ordering of your dataset by applying an explicit sort to it. Similarly, any issues with algorithms that include randomness can be avoided by setting the random seed before performing the corresponding operation. Section 11.2.3. Design tasks using functional paradigms. One approach that may help in creating your tasks is to design them according to the paradigm of functional programming. Functional programming is an approach to building computer programs that essentially treats computation as the application of mathematical functions, while avoiding changing state and mutable data. Additionally, functions in functional programming languages are typically required to be pure, meaning that they may return a result but otherwise do not have any side effects. One of the advantages of this approach is that the result of a pure function in a functional programming language should always be the same for a given input. As such, pure functions are generally both idempotent and deterministic, exactly what we are trying to achieve for our tasks in Airflow functions. Therefore, proponents of the functional paradigm have argued that similar approaches can be applied to data processing applications, introducing the functional data engineering paradigm. Functional data engineering approaches essentially aim to apply the same concepts from functional programming languages to data engineering tasks. This includes requiring tasks to not have any side effects and to always have the same result when applied to the same input dataset. The main advantage of enforcing these constraints is that they go a long way toward achieving our ideals of idempotent and deterministic tasks, thus making our DAGs and tasks reproducible. For more details, refer to this blog post by Maxime Beauchamont, one of the key people behind Airflow, which provides an excellent introduction to the concept of functional data engineering for data pipelines in Airflow. See this link. Section 11.3, Handling Data Efficiently. DAGs that are meant to handle large amounts of data should be carefully designed to do so in the most efficient manner possible. In this section, we'll discuss a couple of tips on how to handle large data volumes efficiently. Section 11.3.1, Limit the amount of data being processed. Although this may sound a bit trivial, the best way to efficiently handle data is to limit your processing to the minimal data required to obtain the desired result. After all, processing data that is going to be discarded anyway is a waste of both time and resources. In practice, this means carefully thinking about your data sources and determining if they are all required. For the data sets that are needed, you can try to see if you can reduce the size of them by discarding rows, columns that aren't used. Performing aggregations early on can also substantially increase performance, as the right aggregation can greatly reduce the size of an intermediate data set, thus decreasing the amount of work that needs to be done downstream. To give an example, imagine a data process in which we are interested in calculating the monthly sales volumes of our products among a particular customer base, figure 11.5. In this example, we can calculate the aggregate sales by first joining two data sets, followed by an aggregation and filtering step in which we aggregate our sales to the required granularity, then filtered for the required customers. A drawback of this approach is that we are joining two potentially large data sets to get our result, which may take considerable time and resources. A more efficient approach is to push the filtering aggregation steps forward, allowing us to reduce the size of the customer and sales datasets before joining them. This potentially allows us to greatly reduce the size of the joined dataset, making our computation much more efficient. Although this example may be a bit abstract, we have encountered many similar cases where smart aggregation or the filtering of datasets, both in terms of rows and columns, greatly increase the performance of the involved data processes. As such, it may be beneficial to carefully look at your DAGs and see if they are processing more data than needed. Section 11.3.2, Incremental Loading, Processing. In many cases, you may not be able to reduce the size of your dataset using clever aggregation or filtering. However, especially for time series datasets, you can often also limit the amount of processing you need to do in each run of your processing by using incremental data processing. The main idea behind incremental processing, which we touched on in Chapter 3, is to split your data into time-based partitions and process them individually in each of your DAG runs. This way, you limit the amount of data being processed in each run to the size of the corresponding partition, which is usually much smaller than the size of the entire dataset. However, by adding each run's results as increments to the output dataset, you still build up the entire dataset over time. Figure 11.6. An advantage of designing your process to be incremental is that any error in one of the runs won't require you to redo your analysis for the entire dataset. you can simply restart the run that failed. Of course, in some cases, you may still have to do analyses on the entire dataset. However, you can still benefit from incremental processing by performing filtering aggregation steps in the incremental part of your process and doing the large-scale analysis on the reduced result. Section 11.3.3 Cache Intermediate Data. In most data processing workflows, DAGs consist of multiple steps that each perform additional operations on data coming from preceding steps. An advantage of this approach, as described earlier in this chapter, is that it breaks our DAG down into clear, atomic steps, which are easy to rerun if we encounter any errors. However, to be able to rerun any steps in such a DAG efficiently, we need to make sure that the data required for those steps is readily available, figure 11.7. Otherwise, we wouldn't be able to rerun any individual step without also rerunning all its dependencies, which defeats part of the purpose of splitting our workflow into tasks in the first place. A drawback of caching intermediate data is that this may require excessive amounts of storage if you have several intermediate versions of large datasets. In this case, you may consider making a trade-off in which you only keep intermediate datasets for a limited amount of time, providing you with some time to rerun individual tasks should you encounter problems in recent runs. Regardless, we recommend always keeping the rawest version of your data available. For example, the data you just ingested from an external API. This ensures you always have a copy of the data as it was at that point in time. This type of snapshot versioning of data is often not available in source systems, such as databases, assuming no snapshots are made, or APIs. Keeping this raw copy of your data around ensures you can always reprocess it as needed. For example, whenever you make changes to your code, or if any problems occurred during the initial processing. Section 11.3.4 Don't store data on local file systems. When handling data within an Airflow job, it can be tempting to write intermediate data to a local file system. This is especially the case when using operators that run locally on the Airflow worker, such as the Bash and Python operators, as the local file system is easily accessible from within them. However, a drawback of writing files to local systems is that downstream tasks may not be able to access them because Airflow runs its tasks across multiple workers, which allows it to run multiple tasks in parallel. Depending on your Airflow deployment, this can mean that two dependent tasks, that is, one task expects data from the other, can run on two different workers, which do not have access to each other's file systems and are therefore not able to access each other's files. The easiest way to avoid this issue is to use shared storage that can be accessed in the same manner from every Airflow worker. For example, commonly used pattern is to write intermediate files to a shared cloud storage bucket, which can be accessed from each worker using the same file URLs and credentials. Similarly, shared databases or other storage systems can be used to store data, depending on the type of data involved. Section 11.3.5 Offload work to external source systems. In general, Airflow really shines when it's used as an orchestration tool, rather than using the Airflow workers themselves to perform actual data processing. For example, with small datasets, you can typically get away with loading data directly on the workers using the Python operator. However, for larger datasets, this can become problematic, as they will require you to run Airflow workers on increasingly larger machines. In these cases, you can get much more performance out of a small Airflow cluster by offloading your computations or queries to external systems that are best suited for that type of work. For example, when querying data from a database, you can make your work more efficient by pushing any required filtering, aggregation, to the database system itself, rather than fetching data locally and performing the computations in Python on your worker. Similarly, for big data applications, you can typically get better performance by using Airflow to run your computation on an external Spark cluster. The key message here is that Airflow was primarily designed as an orchestration tool, so you'll get the best results if you use it that way. Other tools are generally better suited for performing the actual data processing, so be sure to use them for doing so, allowing the different tools to each play to their strengths. Section 11.4 Managing your resources. When working with large volumes of data, it can be easy to overwhelm your Airflow cluster or other systems used for processing the data. In this section, we'll dive into a few tips for managing your resources effectively, hopefully providing some ideas for managing these kinds of problems. Section 11.4.1. Managing concurrency using pools. When running many tasks in parallel, you may run into situations where multiple tasks need access to the same resource. This can quickly overwhelm said resource if it is not designed to handle this kind of concurrency. Examples can include shared resources like a database or GPU system, but can also include Spark clusters if, for example, you want to limit the number of jobs running on a given cluster. Airflow allows you to control how many tasks have access to a given resource using resource pools, where each pool contains a fixed number of slots, which grant access to the corresponding resource. Individual tasks that need access to the resource can be assigned to the resource pool, effectively telling the Airflow scheduler that it needs to obtain a slot from the pool before it can schedule the corresponding task. You can create a resource pool by going to the Admin Pools section in the Airflow UI. This view will show you an overview of the pools that have been defined within Airflow, figure 11.8. To create a new resource pool, click Create. In the new screen, figure 11.9, you can enter a name and description for the new resource pool, together with the number of slots you want to assign to it. The number of slots defines the degree of concurrency for the resource pool. This means that a resource pool with 10 slots will allow 10 tasks to access the corresponding resource simultaneously. To make your tasks use the new resource pool, you need to assign the resource pool when creating the task. This way, Airflow will check to see if any slots are still available in my_resource_pool before scheduling the task in a given run. If the pool still contains free slots, the scheduler will claim an empty slot, decreasing the number of available slots by 1, and schedule the task for execution. If the pool does not contain any free slots, the scheduler will postpone scheduling the task until a slot becomes available. Section 11.4.2. Detecting long-running tasks using SLAs and alerts. In some cases, your tasks or DAG runs may take longer than usual due to unforeseen issues in the data, limited resources, and so on. Airflow allows you to monitor the behavior of your tasks using its SLA, Service Level Agreement, mechanism. This SLA functionality effectively allows you to assign SLA timeouts to your DAGs or tasks, in which case Airflow will warn you if any of your tasks or DAGs misses its SLA, that is, takes longer to run than the specified SLA timeout. At the DAG level, you can assign an SLA by passing the SLA argument to the default_args of the DAG. By applying a DAG level SLA, Airflow will examine the result of each task after its execution to determine whether the task's start or end time exceeded the SLA compared to the start time of the DAG. If the SLA was exceeded, Airflow will generate an SLA miss alert, notifying users it was missed. After generating the alert, Airflow will continue executing the rest of the DAG, generating similar alerts for other tasks that exceed the SLA. By default, SLA misses are recorded in the Airflow Metastore and can be viewed using the web UI under Browse SLA Misses. Alert emails are also sent to any email addresses defined on the DAG using the email DAG argument, warning users that the SLA was exceeded for the corresponding task. You can also define custom handlers for SLA misses by passing a handler function to the DAG using the SLA_miss_callback parameter. It is also possible to specify task-level SLAs by passing an SLA argument to a task's operator. This will only enforce the SLA for the corresponding tasks. However, it's important to note that Airflow will still compare the end time of the task to the start time of the DAG when enforcing the SLA, rather than the start time of the task. This is because Airflow SLAs are always defined relative to the start time of the DAG, not to individual tasks. Summary. Adopting common style conventions together with supporting linting, formatting tools can greatly increase the readability of your DAG code. Factory methods allow you to efficiently generate recurring DAGs or task structures while capturing differences between instances in small configuration objects or files. Idempotent and deterministic tasks are key to building reproducible tasks and DAGs, which are easy to rerun and backfill from within Airflow. Concepts from functional programming can help you design tasks with these characteristics. Data processes can be implemented efficiently by carefully considering how data is handled, that is, processing in the appropriate systems, limiting the amount of data that is loaded, and using incremental loading, and by caching intermediate data sets in available file systems that are available across workers. You can manage, limit access to your resources in Airflow using resource pools. Long-running tasks, DAGs, can be detected and flagged using SLAs. Chapter 12. Operating Airflow in Production. This chapter covers dissecting the Airflow scheduler, configuring Airflow to scale horizontally using different executors, monitoring the status and performance of Airflow visually, sending out alerts in case of task failures. In most of the previous chapters, we focused on various parts of Airflow from a programmer's perspective. In this chapter, we aim to explore Airflow from an operations perspective. A general understanding of concepts such as distributed software architecture, logging, monitoring, and alerting is assumed. However, no specific technology is required. Configuring Airflow. Throughout this chapter, we often refer to the Airflow configuration. Configuration in Airflow is interpreted in this order of preference. 1. Environment variable, Airflow_section_key. 2. Command environment variable, Airflow_section_key_cmd. 3. In Airflow.cfg. 4. Command in Airflow.cfg. 5. Default value. Whenever referring to configuration options, we will demonstrate option 1. For example, take the configuration item web_server_port in the web server section. This will be demonstrated as Airflow_web_server_web_server_port. To find the current value of any configuration item, you can scroll down in the Configurations page in the Airflow UI down to the table Running Configuration, which shows all configuration options, their current value, and from which of the 5 options the configuration was set. Section 12.1. Airflow Architectures. At a minimum, Airflow consists of 3 components, Figure 12.1. Web server, scheduler, database. The web server and scheduler are both Airflow processes. The database is a separate service you have to provide to Airflow for storing metadata from the web server and scheduler. A folder with DAG definitions must be accessible by the scheduler. Web server and DAG's deployment in Airflow 1. In Airflow 1, the DAG files must be accessible to both the web server and scheduler. This complicates deployment because sharing files between multiple machines or processes is not a trivial task. In Airflow 2, DAGs are written in a serialized format in the database. The web server reads this serialized format from the database and does not require access to the DAG files. Serialization of DAGs has been possible since Airflow 1.10.10, although it is optional. To enable DAG serialization in Airflow 1, greater than or equal to 1.10.10 only, you must configure the following: Airflow_core_store_dag_code equals true. Airflow_core_store_serialized_dags equals true. The web server's responsibility is to visually display information about the current status of the pipelines and allow the user to perform certain actions, such as triggering a DAG. The scheduler's responsibility is twofold. 1. Parse DAG files, that is, read DAG files, extract bits and pieces, and store these in the metastore. 2. Determine tasks to run and place these tasks on a queue. We will dive deeper into the scheduler's responsibilities in section 12.1.3. Airflow can be installed in various ways, from a single machine, which requires minimal effort to set up but is not scalable, to multiple machines, which requires more initial work but has horizontal scalability. In Airflow, the different execution modes are configured by the type of executor. At the time of writing, there are 4 types of executors. Sequential executor, default. Local executor. Celery executor. Kubernetes executor. The type of executor is configurable by setting airflow_core_executor to one of the executor types from the list, table 12.1. Let's look at how these 4 executors operate internally. Section 12.1.1. Which executor is right for me? The sequential executor is the simplest and the one you get automatically with Airflow. As the name implies, it runs tasks sequentially. It is mainly used for testing and demo purposes and will run tasks rather slowly. It will only operate on a single machine. The next step, while remaining on a single machine, is the local executor, which is not limited to a single task at a time, but can run multiple tasks in parallel. Internally, it registers tasks to execute in a Python FIFO, first in, first out, queue, which worker processes read and execute. By default, the local executor can run up to 32 parallel processes. This number is configurable. If you want to distribute your workloads over multiple machines, you have 2 options, the Celery executor and the Kubernetes executor. Distributing work over multiple machines can be done for various reasons. You're hitting the resource limits of a single machine, you want redundancy by running jobs on multiple machines, or you simply want to run workloads faster by distributing the work across multiple machines. The Celery executor internally applies Celery, see this link, as the mechanism for queuing tasks to run, and workers read and process tasks from the queue. From a user's perspective, it works the same as the local executor by sending tasks to a queue, and workers read tasks and process from the queue. However, the main difference is that all components can run on different machines, spreading the workload. Currently, Celery reports RabbitMQ, Redis, and AWS SQS for the queuing mechanism, called the broker in Celery terms. Celery also comes with a monitoring tool named Flower for inspecting the state of the Celery system. Celery is a Python library and thus nicely integrates with Airflow. For example, the CLI command airflow celery worker will actually start a Celery worker. The only real external dependency for this setup is the queuing mechanism. Lastly, the Kubernetes executor, as the name implies, runs workloads on Kubernetes. See this link. It requires the setup and configuration of a Kubernetes cluster on which to run Airflow, and the executor integrates with the Kubernetes APIs for distributing Airflow tasks. Kubernetes is the de facto solution for running containerized workloads, which implies every task in an Airflow DAG is run in a Kubernetes pod. Kubernetes is highly configurable and scalable, and is often already in use within an organization. Therefore, many happily use Kubernetes in combination with Airflow. Section 12.1.2. Configuring a metastore for Airflow. Everything that happens in Airflow is registered in a database, which we also refer to as the metastore in Airflow. A workflow script consists of several components, which the scheduler interprets and stores in the metastore. Airflow performs all database operations with the help of SQL Alchemy and Python ORM, Object Relational Mapper, framework, for conveniently writing Python objects directly to a database without having to manually write out SQL queries. As a result of using SQL Alchemy internally, only databases supported by it are also supported by Airflow. From all supported databases, Airflow recommends using PostgreSQL or MySQL. SQLite is also supported, but only in combination with the sequential executor, as it does not support concurrent writes and is therefore not suitable for a production system. It is, however, very convenient for testing and development purposes due to its easy setup. Without any configuration, running airflow db init creates a SQLite database in $airflow_home/airflow.db. In case you want to set up a production system and go with MySQL or Postgres, you must first create the database separately. Next, you must point Airflow to the database by setting airflow_core_SQL_alchemy_con. The value of this configuration item should be given in URI format like this. See the following examples. MySQL, see this link. PostgreSQL, see this link. The Airflow CLI provides 3 commands for configuring the database. Airflow db init, create the Airflow database schema on an empty database. Airflow db reset, wipe any existing database and create a new empty database. This is a destructive operation. Airflow db upgrade, apply missing database schema upgrades if you've upgraded the Airflow version to the database. Running db upgrade on an already upgraded database schema will result in no action and is therefore safe to execute multiple times. In the case no database has been initialized, the effect will be the same as db init. Note, however, that it does not create default connections as db init does. Running any of these database commands will print something like the following. What you see is the output of Alembic, another Python database framework for scripting database migrations. Each line in listing 12.1 is the output of one single database migration. If you upgrade to a newer Airflow version that contains database migrations, whether or not a new version contains database upgrades is listed in the release notes. You must also upgrade the corresponding database. Running Airflow db upgrade will check at which migration step your current database lives and apply the migration steps that were added in the new release. At this stage, you have a fully functional Airflow database and can run Airflow web server and Airflow scheduler. When opening the web server on this link, you will see many example _* DAGs and connections, figure 12.2. These examples might come in handy during development, but are likely not desirable for a production system. You can exclude example DAGs by setting airflow_core_load_examples equals false. However, upon restarting the scheduler and web server, you will probably be surprised to still see the DAGs and connections. The reason is that setting load_examples to false tells Airflow to not load example DAGs, does not apply to connections, and Airflow will not reload them. However, already loaded DAGs remain in the database and are not deleted. The same behavior applies to default connections, which can be excluded by setting airflow_core_load_default_connections equals false. With this in mind, a clean, that is, no examples, database is achieved by completing the following steps. 1. Install Airflow. 2. Set Airflow_core_load_examples equals false. 3. Set Airflow_core_load_default_connections equals false. 4. Run Airflow db init. Section 12.1.3, a closer look at the scheduler. To understand how and when tasks are executed, let's take a closer look at the scheduler. The scheduler has multiple responsibilities. Parsing DAG files and storing extracted information in the database. Determining which tasks are ready to execute and placing these in the queued state. Fetching and executing tasks in the queued state. Airflow runs all tasks in DAGs within a job. Although job classes are internal to Airflow, you can view the running jobs in the Airflow UI. The scheduler also runs in a job, albeit its own special job, namely a scheduler job. All jobs can be inspected in the Airflow UI under Browse, Jobs, figure 12.3. The scheduler job has 3 responsibilities. First, it's responsible for parsing DAG files and storing extracted information in the database. Let's inspect what that entails. The DAG processor. The Airflow scheduler periodically processes Python files in the DAGs directory, the directory set by airflow_core_dags_folder. This means that even if no change was made to a DAG file, it periodically evaluates each DAG file and persists the found DAGs in the Airflow metastore, because you can create dynamic DAGs that change structure based on an external source in Airflow while the code stays the same. An example is a DAG in which a YAML file is read and tasks are generated based on the content of it. In order to pick up changes in dynamic DAGs, the scheduler reprocesses DAG files periodically. Footnote 1. While there are ongoing discussions in the Airflow community to make the DAG parsing event-based by listening for